Okay, in this video, we're going to talk about how do chemists actually know how many particles they're working with? Because atoms are so very, very small. How do we know how many we are? We don't have microscopic little tweezers that we can go 1 atom, 2 atoms, 3 atoms. What we do instead is that we weigh our samples, and then we can, from the weight, we can get a count. Now, the concept that's going to allow us to go from how much does it weigh to how many things do I have is called the mole. I want you to think about the mole as a bridge. It's a concept that bridges this idea of how much does it weigh and how many are there. So, okay, first of all, what is a mole? A mole is, if I can borrow a term, 602 hexillion. That's actually a number, but you can see it written in the bottom part of this slide, 6.022 times 10 to the 23rd things. Now this is actually a measurement that I've just given you with 4 sig figs. Depending on the reference you use, you may have more or less sig figs. I like to use at least 4 sig figs in my conversion factor or in my measurement for how many things are in a mole when I am looking at doing conversions that have at least 3 digits in the mass numbers. You could go to a source like Wikipedia and figure out how many moles there are, how many particles there are in a mole with more digits than that. So one thing that I like to do in a calculator that I use frequently is I like to store the number, Avogadro's number, into one of the retrieval buttons in the memory using, and I usually store it under n because Avogadro's number is often said n subscript a. So there you go, 6.022 times 10 to the 23rd. So I want you to think of this number very much like a chemist dozen. It tells us how many things are in a mole. So for example, we're used to working with a dozen. If I was to say I have a dozen eggs, we know that means that there's 12 eggs. Now notice I'm being very particular here that I'm actually putting a unit because I don't want to say 12 parts of eggs because then it's like, well, what's a part of an egg? Is it a yolk? Is it a white? Is it shell? So it's 12 whole eggs. If I have a dozen cookies, that's 12 cookies. If they're chocolate chip cookies, it doesn't mean that there's 12 chocolate chips, unless you make cookies like my grandma used to. But a dozen cookies, 12 cookies. So when I talk about a mole of carbon, what I'm really talking about is 6.022 times 10 to the 23rd particles of carbon. And what we call that particle of carbon is an atom. So this idea of a particle, you know, the exact name on it, is it an atom? Is it a molecule? We want to be very specific. So in our first, in the lab 0, when we did the classification of matter, we talked about what a particle was. And a particle could be a molecule or an atom, or it could be something else, just depending on what classification of matter it is. So if it's an element, we're talking about an atom. Unless it's a diatomic molecule. If it's a compound, we talk about how many molecules there are. So here we have a compound. Now this is actually an ionic compound, and now that we've done our chapter 2 on ionic compounds, I should know the difference between a molecule and this formula unit, because NaCl just means that's the simplest ratio. So I'm going to use this number, 6.022 times 10 to the 23rd, how many units of sodium chloride. I'm not really going to call it a molecule because it's the wrong type of compound. It's not a molecular compound. But it's the same concept and the number's going to be the same. And mathematically, I'm going to treat it the same. So if I'm working with sugar, then the terminology of molecule is appropriate. Now, sometimes this can get confusing for students because, you know, mathematically, we treat a formula unit and a molecule the same thing, even though conceptually they are different. If I'm going to draw particulate models, they won't look exactly the same. But mathematically, we can treat that. So we know how many particles a mole has because a mole always has the same number of particles. It doesn't matter what it is. Just like a dozen always has 12 things, and it doesn't matter what we define that thing as. Okay, so if I was going to look at, just take this concept and think about how much sand do I have. If I have a mole of sand, that would be 6.022 times 10 to the 23rd particles of sand. And I'm thinking, well, what word could I use to describe a particle of sand? I don't want to call it a molecule. I don't want to call it an atom of sand. That doesn't make sense. Maybe a grain of sand would be appropriate. So you just want to adjust your vocabulary when you're talking about your particles to be appropriate to what you're talking about. Okay, so how do we use this concept to go about counting a sample if we know the mass? We need to look at the periodic table and look at these mass units that are in the periodic table. So for example, when we look at hydrogen, hydrogen here has a 1.01 next to it. That is the mass value. Now there's two interpretations that we can give to this mass value. I can think about that this is the mass of one atom. So I can say that one atom of hydrogen is equal to 1.01 if the unit I use is an atomic mass unit. Okay, so if I'm thinking small, atomic level small, I can look at what is the mass of a single molecule. So I could say 1 molecule of hydrogen is equal to 2.02 atomic mass units. If I'm talking about, that's because I doubled it, okay? So 1 molecule of nitrogen has 2 nitrogens in it. 1 molecule of nitrogen would equal 28.02 atomic mass units, and 1 molecule of NH3 is equal to, if I add 14 plus 3 hydrogens, that would be 17.04 atomic mass units. So then if I want to calculate how much does a molecule weigh, I could simply use this conversion factor that says what is an atomic mass unit. An atomic mass unit is 1.6605 times 10 to the minus 24th grams, and I could just do that the whole on every single one of them, and I would know what the weight of a molecule was in grams. So just depending on what scale you want to use. Now, this is too small of a sample to get out there. So what we're going to do next is we're going to look at what this is, and if I scale everything up to mole quantities. So another way that I could look at this is that if I took that molecule, if I said 1 molecule of H2 is equal to 2.02 AMUs. And actually, let's go back a screen and just calculate what that is in grams. So 2.02 times times 1.6605 times 10 to the minus 24th. That would give me 3.35 times 10 to the minus 24th grams would equal 1 molecule. Okay, so now what I want to do now is I am going to multiply both sides of this by the mole quantity. So actually, let's do this. If I say, just based on what I had before, because we just figured out 1 molecule of hydrogen is equal to 3.35 times 10 to the minus 24th grams, because I just figured that out. Okay, now what I want to do is that I want to multiply both sides of this equation by Avogadro's number. If I multiply the left-hand side by Avogadro's number and the right-hand side by Avogadro's number, then what I have is 6.022 times 10 to the 23rd molecules of hydrogen. Molecules of hydrogen is equal to, I got to multiply both sides, times 10 to the 23rd equals 2.02 grams. Okay, so what does that mean? It means that 1 mole of hydrogen is equal to 2.02 grams. So what does that mean, just as a shorthand? So what did I just do? I can interpret this periodic table one of two ways. Either I can say that the number that is given in the box for the AMUs, for the mass, is either, I can say it's 1 atom equals blank AMUs, or I could say that 1 mole of this is equal to whatever that value on the periodic table is in grams. So it's just a convenient way that we do it. We just scaled everything up by a mole. Okay, so here we go. Look at the periodic table here, and I am interpreting this value. So first of all, notice what's the same. On the atomic level, oh, I did the wrong thing there. Let me fix it. (2.02 AMUs). On the mole scale, notice that the value stays the same. Okay, if it's 28.02 on the atomic scale, it's 28.02 on the mole scale. If it's 17.04 on the AMU scale, it's 17.04 on the gram mole scale. So what's different here is that on the atomic scale, it's AMUs per molecule, and on the mole scale, it is grams per mole. Grams per mole, grams per mole. Okay, so let's take a look again then about this idea of a bridge. So here is my two sides of the bridge, things that I have. I might know how many particles I have. Let me get a different color here. I might know how many particles I have. I might know how many grams I have. And I can go in between these if I have a concept of moles. So this is how I like to interpret this mole map, if you will, that everything that I've got in a box, this is a measure. This is a measurement. And then everything that I have in my arrows is a conversion factor. So if you think about when we do a unit analysis, that in a unit analysis what you do is you take a measurement and you multiply it by a conversion factor. Then I'm going to get another measurement. Okay, so if I think about this with using this map, if I have grams, that's a measurement. If I want moles, that's another measurement. I need one conversion factor to do that. The conversion factor that I'll need to go from grams to moles is this number, blank grams is 1 mole, and you're going to pull that number off of the periodic table. If you have mass and you want number of particles, then I have to go to the bridge measurement, which is the mole. So that will require you going from grams, use the conversion factor in yellow, grams to moles to get the measurement of moles. Then I'll need a second conversion factor to go to numbers of particles. So let's use an example. Let's do some examples. Okay, so when we look at calcium nitrate, so this is where we, the stuff that we did on nomenclature in chapter 2 is going to come back to us. So we have to look at calcium nitrate and know the formula. So based on a periodic table, let's just take a look at the periodic table for calcium nitrate. Let me erase all the ink on this slide. So here we have calcium and nitrate is NO3 negative. So calcium's a +2. Nitrate is NO3. So if I want to get the molar mass here, it's going to be 40.08 plus nitrogen, 14.01 plus 3 oxygens. And then I have to multiply that whole thing by 2. And I'll get the molar mass of I get 164.1. Okay, so what does that number 164.1 mean? It can mean in 1 mole of calcium nitrate, there's going to be 164.1 grams of calcium nitrate. So the periodic table that I'm using is actually reporting everything out to the second place after the decimal, so I'm just going to make sure that I'm being consistent. So 164.10. So let's make sure that I've got that at the ready. Okay, so now I'm going to do some conversions factors. So one, how many moles do I have? So I'm going to look at my mole bridge. So I'm just going to think about the concept here that my mole is in the middle, and it's a bridge between my grams and my units, my formula units of calcium nitrate. Okay, so that's my relationship. So how many moles? So this is my conversion factor, 164.1. So I'm going to say my measurement is 37.6 grams of calcium nitrate. Then I'm going to multiply it by my conversion factor, which is 164.10 grams in 1 mole. So that would be 0.229 moles of calcium nitrate. And again, I'm going to round to 3 sig figs because the original measurement has 3. Okay, now we're going to do the next question, how many formula units I have. Well, if I take again a look at how many formula units I have, I already know how many moles I have, and a formula unit is a particle. So I know a relationship that if I have 1 mole of calcium nitrate, that's equal to 164.10 grams. But on the other side, as my bridge, I can say it's equal to 6.022 times 10 to the 23rd units, or formula units. Often I'll just say units of calcium nitrate. Okay, so I already know that I've got 0.229. I could do this lots of ways because I have lots of measurements here. But I know that my measurement, I'm going to start with my original measurement. I have 37.6 grams of calcium nitrate. I have 164.10 grams in 1 mole of calcium nitrate. And then I know that if I have 1 mole of calcium nitrate, I have 6.022 times 10 to the 23rd units of calcium nitrate. So I've already done the first part, so I just have that already in my calculator stack. So I've already got that as being actually I didn't do it all the way through. So 37.6 divided by 164.1. Okay, so I've already got that in my calculator stack. So I'm not going to delete that. All I'm going to do here is now take that value and I'm going to multiply it by 6.022 times 10 to the 23rd. So I'm just taking the previous answer, multiplying it by 6.022 times 10 to the 23rd, and I'm going to get 1.38 times 10 to the 23rd units of calcium nitrate. Okay, now we're going to go do some further calculations here. So now, again, let's just keep in, I'm going to draw that mole map again, that we have, I know that there is, I can say that 1 mole of calcium nitrate, this is another way of drawing the mole bridge, is 164.10 grams, and I can say that it's equal to 6.022 times 10 to the 23rd units. Okay, so they're showing the mole as the bridge between those. Now I want to look at how many atoms they have. Now the problem here is that I don't have a relationship yet that talks about atoms. I know how many units of calcium nitrate there are if I have grams of calcium nitrate, but I need a bridge that we'll talk about. How do I bridge the idea of calcium nitrate to plain old atoms? Well, I have to think about what this particulate model would look like. When I'm talking about calcium nitrate, what is calcium nitrate? Calcium nitrate is 1 calcium plus 2 nitrogens plus 6 oxygen atoms. So what I've really got there, 6, 7, 8, there's 9 atoms. So that's another relationship. You have to have 9 atoms in order to make 1 unit of calcium nitrate. So this just becomes another unit analysis type question. So I've got 37.6 grams of calcium nitrate, and I can relate the grams of calcium nitrate to the moles of calcium nitrate. There's 164.1. And then I can relate the moles of calcium nitrate to 6.02 times 10 to the 23rd. I'm just going to put N sub A units of calcium nitrate. And then here's my latest step right here. So in this final thing, I'm going to say if I have 1 unit of calcium nitrate, I'm going to have 9 atoms. It takes 9 atoms to make 1 unit. So if I look at the work that I've already done on my calculator, I've already done step 1 and step 2. I already have those in my stack. I think it's a bad habit to be clearing your calculator every time. So those first 2 steps would give me the number on my calculator display right now. So all I need to do is multiply that by 9, and I would get 1.24 times 10 to the 24th atoms. Okay, so in my final one, the last question, I kind of ran over it, so I'm just going to write down what it is I want to know how many nitrogen atoms. Well, I need to relate the nitrogen atoms to something, so I just need to come up with a rational statement here. And I'm going to look at I'm going to go back to my units of calcium nitrate, and I'm going to say if I have 1 unit of calcium nitrate, that I need 2 nitrogen atoms, because that's how you build it. So again, I'm going to start this problem out identical to what I did in this first bit, and I'm just going to change the last statement to be about nitrogen atoms instead of total nitrogen. So bear with me. 37.6 grams of calcium nitrate. (164.1 grams in 1 mole. 1 mole is Avogadro's number of units. And then if I have 1 unit, it's going to have 2 nitrogen atoms. So I'm going to go back into my stack and grab that number that I had with what I've boxed up here. So if I get that far, that's the 1.38 times 10 to the 24th, and I'm just going to double it. And I'm going to get 2.76 6 times 10 to the 23rd nitrogen atoms. Okay. All right, so hopefully that gives you some strategies. I'm also going to link into the module some other people doing some conversions here, but I wanted to give you this overview and just be thinking about in general that we are going to be looking at using this mole idea as a bridge between grams and units of whatever you're talking about.